We can explain how machine learning works through a popular saying that simply yet effectively represents the human ability to infer knowledge from experience. Let's take the Italian saying Rossa di sera bel tempo si spera, in English, red sky at night, shepherd's delight. This proverb reflects the human ability to observe the environment, gather examples, build a knowledge base, and draw useful conclusions from it. In this case, the repeated observation of a red sky at sunset was, in most cases, associated with the following day of good weather. What did he basically do? He collected data, he observed patterns. He formulated a mental model based on experience. And what's even more interesting, he expressed this knowledge in a probabilistic form. That hopeful Z-spera is emblematic because it acknowledges that the prediction isn't certain, but highly probable. Machine learning works in a very similar way. It gathers data, analyzes it, builds a model, and generates predictions. Here, too, there is always a margin of error that the technique tries to reduce. But it can never be completely eliminated. This margin is what makes the model flexible, able to handle situations it has never seen before. In fact, we are wary of models that seem to work 100% of the time because it's unlikely they've truly encountered all the possible variables and scenarios of the real world. A model that's too perfect runs the risk of being overfitted to known data, losing its ability to generalize. In short, machine learning is a way to turn experience into prediction, just like we do every day when we learn to recognize patterns in the world around us. In 1943, McCulloch and Pitts took a fundamental step in the history of artificial intelligence. They tried to build a mathematical model that would reproduce the functioning of the biological neuron. The biological neuron, to put it simply, is made up of dendrites that receive signals from other neurons, a nucleus that processes the information, and an axon that transmits the processed signal to other neurons. The idea behind the artificial neuron is to mimic this behavior. The inputs represent the incoming information, for example, the temperature of a room, atmospheric pressure, or the observation of the sky. Each input is assigned a weight that indicates its importance. These weighted inputs are then processed by a function inside the neuron's nucleus, and the result is transmitted as output. When multiple artificial neurons are connected to each other, a neural network is formed. The neurons are organized into levels or layers. Each layer receives the output from the previous one, processes it, and passes it on to the next. For a neural network to work properly, a training process is necessary. During this phase, the network is taught to perform a specific task using large amounts of data. Let's suppose, for example, that we want to teach the network to recognize whether there is a dog or a cat in an image. We provide an image to the network, which will return a prediction. If the prediction is correct, no intervention is needed. If, on the other hand, the prediction is wrong, the weights of the connections between the neurons are adjusted by changing the numerical values that control the flow of information. This procedure is repeated hundreds, thousands, even millions of times until the neural network becomes a probabilistic model capable of representing the studied domain. At that point, given a new image, the network will be able to provide a more or less accurate prediction depending on the quality of the training, the amount of data, and the complexity of the task. In the next section, we will try to understand what determines the effectiveness of a neural network and which factors influence its ability to generalize correctly. For a neural network to be able to distinguish, for example, between a dog and a cat in an image, it needs to see a huge amount of data. It must learn to recognize the distinctive features of each category. By building a model that can generalize from the examples provided. The answer the network provides is never absolute, but probabilistic. For example, It might indicate that an image contains a cat with an 80% probability and a dog with a 20% probability. The system will then choose the option with the highest probability, but it can never guarantee absolute certainty. This process requires an enormous amount of resources, not just in terms of data, but also infrastructure and computational power. In fact, large data archives are needed to store the examples used for training. High computing power is required to process the data and update the models, and both financial and structural resources are necessary to support the entire process. Training neural nets involves countless math operations, or billions of mathematical operations that must be performed quickly. This requires specialized hardware like GPUs or TPUs and an infrastructure capable of providing constant electrical power, efficient cooling, and scalability. In summary, artificial intelligence is not just a product of algorithmic ingenuity, but also the result of significant investments in infrastructure, energy, and technology. It is an ecosystem that lives and grows thanks to an entire supply chain of resources, often invisible but essential.